Now here is the generalization of the relationship between the roots and coefficients of any polynomial equation in general. Now suppose we have this particular polynomial equation. As we can see, there are various terms, and the highest term is x raised to n, that is the nth degree term in x. Now let's consider the roots of this particular equation as alpha 1, alpha 2, alpha 3 and so on up to alpha n. Now we can find out the sum of all these roots, that is denoted by alpha 1 plus alpha 2 plus alpha 3 and so on plus alpha n. So we can denote this particular sum in short as summation of alpha 1. Okay, it's just customary to write a single root, that is alpha 1, and the summation stands for we are summing up all the roots. Now this sum is given by minus a1 upon a0. So if we see this ratio is nothing but the ratio of these two coefficients, that is minus a1 upon a0. Now moving ahead, if we want to see the sum of product of two roots taken at a time, so it would cover the roots something like alpha 1 alpha 2 plus alpha 1 alpha 3 plus alpha 2 alpha 3 and so on. So there will be all the possible combinations of these products. Now this we denote by compact notation as, say, summation of alpha 1 alpha 2. So we are taking two roots at a time into the product. Now this particular sum is given by a2 upon a0. Now once again, if we look at the coefficient, it is the next coefficient in line but divided by the leading coefficient. Similarly, let's see what happens if we want to take the product of three roots at a time, that is alpha 1 alpha 2 alpha 3 plus maybe alpha 1 alpha 2 alpha 4 plus alpha 2 alpha 3 alpha 4 and so on. So this we will denote by summation of alpha 1 alpha 2 alpha 3. Now here it is given by minus of a3 upon a0. So we'll see that as we go from different sums, the sign is alternately plus and minus. Finally, we want to take the product of all the roots together, so that will be just one particular term, that is the product of all the roots taken together. This will be given by, now the sign here will be dependent on n, whether n is even or odd. So in general we write the sign as minus 1 raised to n, and the last coefficient is an divided by a0. So that's the way we can find out the sum of products of various numbers of roots taken at a time. Now let us see a couple of important facts about these polynomial equations in general, that is not only applicable to quadratic equation but any polynomial equation in general. So the first one is a polynomial equation of nth degree has n roots, which may be real or imaginary, but this is an important consequence of the fundamental theorem of algebra, that is an equation of nth degree has at least one complex root. So it follows that there are n complex roots in all, out of which some might be purely real and the rest might be imaginary. The second one is, if all the coefficients of the polynomial equation are real, then the imaginary roots will always occur in conjugate pairs, that is the number of imaginary roots will always be even. And the third property is saying that if degree of the equation, that is n, is odd, then there are odd number of real roots. So in other words, it means that there is at least one real root, because if the degree is odd, then it must have at least one real root, so that the remaining roots could be imaginary since they occur in pairs. So these facts we have to keep in mind while solving the examples. Now let's see how to form a quadratic equation if we are given the roots. That is, say alpha and beta are the roots of a quadratic equation. Then that quadratic equation can be simply written as the product of corresponding two factors, which is x minus alpha into x minus beta equal to 0. So if we expand these two brackets, we will ultimately get the equation x square minus into bracket alpha plus beta times x plus alpha into beta equal to 0. So here we see that the middle coefficient, that is the coefficient of x, is nothing but negative of sum of roots, whereas the last coefficient, that is nothing but the constant term, is nothing but the product of roots. So even if we are not given the roots directly, but suppose we are given the sum and product of those roots, still we can write the direct equation as shown here.